Now we'll talk about doing a remainder estimate for the alternating series. This one's a little more computationally intensive, so we'll do it on the computer. So let's consider this infinite series. It's minus 1 to the k over 4 to the k times k factorial. And we want to know if it converges. If it does converge, we'd like to find an estimate of its sum. And whenever we estimate something, we'd like to have some idea, and mathematically it's nice to have it be a precise, guaranteed idea of how accurate that estimate is. And here the instruction is find it as an estimate of its sum that's guaranteed to be accurate to within 10 to the minus 8. And there's estimation techniques for lots of situations with series, but for alternating series, it's the simplest case. And we saw that in the first video where the theorem says it's just bounded by the size of the first non-included term, the first neglected term. So let's just double check that all of our stuff applies here. Here, the terms of the sequence are indeed alternating. They are a minus 1 to the something, k or k minus 1 or k plus 1, something that alternates strictly, times a sequence of positive terms, which decrease to 0. Two things to check. One is that each term is smaller than the last in size, and the limit really is going to 0. And that's pretty clear from the denominator increasing to infinity. So again, you have to check that for the convergence test to work and for the estimate to work. But once you have that, all of our stuff applies. So it does converge to what? Well, we're going to sum a few terms, and then we don't have to just hope it's a good estimate. We can actually give a good idea of how good an estimate it is. So we're going to look at these terms, and we just want to see when do the terms get small enough so that we can start using this error estimate. So we just look at the general term, the size, strip off the minus 1 to the k, and let's see if it's less than or equal to 10 to the minus 8. Oh, before I go on, three quick things. One is it can be a k here. This happens to start positive once again because this starts at 0 and this is k, but it really doesn't matter whether it's k, k minus 1, or k plus 1. I just wanted to emphasize that. That's not a crucial thing. The other thing is this is a little bit too finicky. This is the usual thing. If this is true for all k just greater than or equal to like some n, then that's fine. As long as eventually it settles down into strict decrease of size. And really it only has to eventually alternate in order to use the test. Now, we'd like to know that it really alternates all the time, so that even from the first few terms, because if we're lucky, only the first few terms will be necessary to actually get the estimate. So here we really do want to make sure that it's strictly alternating, and it is. Okay, so let's see. Let's do some algebra and a little bit of guesswork to figure out how big k has to be to make this quotient less than 10 to the minus 8th. If it were just powers and polynomials, you could maybe do it strictly algebraically. With factorials, you're probably going to need to do some trial and error. But one way to do it is just give a very rough estimate, maybe a pessimistic estimate for how fast the factorial function grows. Pretty soon, for k just bigger than like 3, or I don't know, 4 or 5, I guess, k factorial is going to be bigger than 3 to the k, because it's a product of 1 times 2 times 3 times 4 times 5 times 6, so the numbers get bigger than 3. So roughly that's going to be something we could use as a guideline. And so, excuse me, the reason that's nice is that then we can use algebra to figure out if it were 1 over 4 to the k times 3 to the k, we could really nail it down. And then we can see, it just gives us a place to start our trial and error. So that would be 1 over 12 to the k. If that's going to, say, equal 10 to the minus 8, as with all inequalities, you usually look at the equality first and see where the boundary case is. So that's a nice little equation with exponents. You do it with a log. If you have log 12 on your calculator, you can just do it straight like this. You might have to do change of base, which is pretty nice to do here if you change it to log 10, because then log 10 of 10 to the 8th is 8. That's easy. But then you need a log 10 of 12, and it works out to about 7.3. So if this, again, were exactly this right size, we would definitely need to go to where the neglected term was the 8th term, or the last term we included was 7. Maybe we get lucky. This wasn't a rough estimate after all. So let's try the neglected term be 7 or 8. Now here's one thing. This is one reason I like using k's for my dummy variables, because I want a letter, I want n to be very specifically, here is the last term I included. And it's really annoying to me that in the book, they have statements where in the very exact same statement, in one of these boxes, they use n as a dummy variable, and then in the next line, they use n as, okay, here's how many terms in the sequence I actually include. Where does k stop? So just a bit pet peeve about, I think it can be confusing. So that's why I'm using n here to mean how many, like what's the maximum k? That's exactly the number I'm going to put here. Okay, so let's look at it. If I put in 4 to the 7 times 7 factorial, and now I'm really using the factorial function exactly, turns out we don't quite get 1 times 10 to the minus 8th. It's just a little bit too big. Okay, so the first neglected term, the n plus 1, needs to be where n plus 1 is 8. That's plenty good. That's quite a bit smaller than 10 to the minus 8th. So the actual last term we include is 7. So remember, you've got to make sure you get it clear. You go up to a certain term. Here that's the 7th term in order so that the next term is smaller than your error bound, because it's the first neglected term that needs to be smaller than your desired error bound. Okay, so and then I just had it sum up these terms. It's, the computer can do that easily, but it's really nothing really very sophisticated. It's just plugging in k equals 0, 1 through 7, and then just adding these guys up. And it turns out to be this funky number, 0.778/8007827. That's guaranteed to be good, in other words, to close to the infinite sum, to within, and we could put 10 to the minus 8 here because that was our original goal, but we might as well say, actually, no, we've achieved better than that. It's within less than 4 times 10 to the minus 9th. Really quite close for not a whole lot of work, summing up just a few terms. That was because this denominator grows quite quickly, powers combined with factorials, and so the size of these terms gets small quickly, and then the alternating series estimate says, that's good, that's enough. As long as the next term is small, we know that the remainder is small. Okay, so I just want to say a couple more things. One is that this isn't usually phrased in the alternating series test, but we know it has this alternation up, down, up, down, up, down, and we know that the last term, if you just actually look at what the term with k equals 7 is, that's negative because of this minus 1 to an odd power. So the last term we added was a negative one, and the first neglected term is positive. So if you think back to that wiggling picture from before, from the first part of this video, we're definitely an underestimate. So we could say this is not only within this error estimate, but I know which side I'm on, which is really kind of nice. Now, as an aside, or something like a preview, a little foreshadowing, turns out I picked one that we actually will have a method to get the exact sum for. Or if you've seen a little power series stuff already, as my students have, you might actually recognize, hey, we have a really confident guess that this is exactly what happens when you put in minus 1/4 into the power series for the exponential function. So in fact, if you take e to the minus 1/4 and let this computer give me 11 decimal places, it does turn out to be very, very close. But notice the 78307, that's just a little bit more than the 78270, I guess I could put there. So that really confirms that this was a good estimate, but a little bit on the low side.